Saxon Algebra 2, Lesson 34. You guys, we are now ready to take on the third type of uniform motion problem. Remember, the first type is the Lord of the Rings. Frodo and Sam go to Mordor, or Frodo and Sam go to Mordor and return to the Shire, scarred deeply for life, or at least Frodo, but you know, they did it. In these problems, the first distance is equal to the second distance. And we can say that distance 1 equals distance 2. And then if we remember this relationship that distance always equals rate times time, then we can change this into the rate times the time of the first trip equals the rate times the time of the second trip. And this becomes our base equation for solving that style of problem. The second type is what I call the Titanics. How am I going to write it in here? Okay, because in these, we've got a ship traveling in the night and going bump with an iceberg. Oops. The distance of one thing and the distance of the other thing have no relationship to each other, but they add up to a known total distance. And the other variation on this is, there's two variations, and you know, possibly more. Here they are together on the raft, Jack and Rose, after the ship has gone down. Rose floats off to safety, and Jack goes away from her down to the bottom of the sea. Technically, that should be going down, but you know, we're going to keep it straight. Again, their distances are different, but they add up to a total that we can figure out or are told. The other variation is Rose traveled partway across the Atlantic on the Titanic, then it sank and she shifted over to another boat. Okay, so in these, the distances don't really have any relationship to each other like they did up here, but they add to a known total that we call K. And so we can substitute these. And there's a base equation for that style. Now, I'm kind of excited because I think I finally thought of the movie that works for type 3. And that is Princess Bride. Because there's a lot of chasing and running around in that movie. And I have to watch it again to come up with the exact scenarios. But there's a lot of chasing, right? Buttercup and Wesley are running through the creepy forest, right? And aren't the bad guys after them at that point? I'm quite sure that they are. We've got the dread. Oh, and there's got to be some scenarios in here that work. So for now, just know that this is a story about people chasing each other, sometimes with head starts, sometimes where one runs and the other one starts from the same place and doesn't quite catch up with them. But in these pictures, we have what we call a gap. Here, K stood for the total of both trips together. Here we use the letter K to stand for the gap, the difference between the two trips. Okay? So in these cases, these have slightly different equations because of the way I drew them. But here, the shorter distance plus the gap equals the longer distance. Right? And let me just switch the numbers on these, and then the second one will work too. The shorter distance plus the gap equals the longer distance. Okay? And then we do the same thing where we substitute this in. R1 T1 plus K equals R2 T2. And there's the base equation that we can use. All right, we have two problems to do in this style. Think Princess Bride. Maybe you guys can think of some scenarios where somebody gets a head start and they have to come farther and catch up. or somebody else. We'll figure that out. But I'm pretty sure Princess Bride is going to help with that. All right, so let's work on some of this style. Millicent began the journey at 6 a.m. at 50 kilometers per hour. Well, there's clock time staring us in the face, and there's some information, we're not going to write it down yet. Beauregard began to chase her at 10 a.m. at 60 kilometers per hour. What time was it when Beauregard got within 40 kilometers of Millicent? Okay, so it's hard at first to figure out what in the heck they're saying. Here's Millicent. She's booking along. She's doing her thing. Beauregard starts. Now, we're supposed to assume it's from the same place, but it doesn't really say that, and that's confusing. It says began to chase her. I mean, I guess we can kind of deduce that, but Micah, be careful. It's easy to overthink these, and no offense, I used to do it too. You are the king of overthinking. So don't go too crazy with it. Tell Hammy to just focus on the basics. All right. And then Beauregard didn't catch all the way up to Millicent. There was still a gap in between them at a certain point. So this is the distance of Millicent, and this is the distance of Beauregard. So the distance of Millicent equals the distance of Beauregard plus that gap that we're calling K. Now I can do my RMTM equals RBTB plus K. That's going to work as a base equation. I put my list down here. You guys, you know I want you to set your problems up exactly like this. Exactly. Don't even think of messing with the perfection of this. I say this not to be like cocky or know-it-all-y, but I literally have been doing these problems, you guys, for 20 years. 20 years, that's longer than you've been alive. I've been teaching these problems over and over again. Millicent and Beauregard have been here before. I think I've taught this book every single year since then. The third level, the advanced mathematics, I haven't taught that every single year, but these lower ones I've taught every single year. So trust me, this is the best way to set them up. Now we're going to go back in and get our information. But the first thing I see, Millicent began the journey at 6 a.m. That means we need clock time. Drama up in here. But I've got my handy dandy chart. John does not know about this chart, you guys. I pulled this one out of my own bag of tricks. Millicent, Beauregard, that's the order we're dealing with them. Start, end, hours. Millicent began the journey at 6 a.m. at 50 kilometers per hour. That's her rate. Beauregard began to chase her at 10 a.m. Well, he slept in. At 60. Ooh, he's going faster. What time was it when Beauregard got within 40 kilometers of Millicent? So that's the gap, 40 kilometers. All right, this one's tricky because we have some information about the time, but we don't know the ending time, and so we don't know the hours. What we do know is that Millicent ran 4 hours longer than Beauregard. So the time of Millicent equals the time of Beauregard plus 4. We're gonna have to add 4 hours to his time to get hers because she ran longer. Beautiful. Now we can work with it. We'll find out how many hours, that's what the solution will tell us, is we'll get their times, and then we'll have to back into their ending times. Ooh, so hard. All right, let's bucket this pumpernickel. I have no idea what that meant. Okay, the rate of Millicent goes here, 50. The time of Millicent, we're saying, is TB plus 4. This was tricky. Woo! Okay, that's my eyes spinning around in my head. Rate of Beauregard, 60. And then time of Beauregard, we can just put that in. Notice that we have the same variable twice, so peace descends over the land because we'll be able to solve it. and then K is 40. All right. If we had two different letters there, we would have trouble, but we rewrote Millicent's time as an expression of Beauregard's time, so yeah, I didn't need to say all that. All right, you understand. Now we're just algebra-ing up it. Okay, so I distributed. I'm going to move this 50 over here, so they subtract. And since I'll have the TBs over here, I'll move the plain numbers over here. That's gone. That's gone. 200 minus 40 is 160 and 10 TB. That means that the time of Beauregard was 16 hours. You guys, what the heck? That's a lot of running. I hope this is not based on real events. So now we have to figure out if they started at 10 a.m. and ran for 16 hours, what time will it be when they stop? Okay, so here's 10 a.m. I'm writing this down so I can figure it out. If I add 2 hours, that will be noon. If I add 12 more hours, that will be midnight. And let's see, that gets me up to 14 hours, so I need 2 more hours, and that would be 2 a.m. That's a total of the 16 hours, right? Scooted that up so it's a little bit better in the light. So this is how my brain worked this out. Start at 10 a.m. First go to noon, that's 2 hours. Then go to midnight, that's another 12. Figure out how many are left. 14 I've accounted for, I have 2 more, so that gets me to 2 a.m. So the final answer is that Beauregard would come within 40K of her at 2 a.m. in the morning. And I think they both need to think about their lives because that's ridiculous. That's too much running, come on. Okay, that's the first example. That's a really hard problem, isn't it? Look how impressive. If you understood that, you're smart. Take it to the bank, you guys. You're smart if you can follow all of that craziness. And now we're just going to do one more, and then you can put your heads down and cry if you want to, because this is a lot. This is one of my favorites, though. I like Millicent and Beauregard, but this one's about Robin Hood, and I'm kind of crazy about that Disney version of Robin Hood. I hope you've seen it. If you haven't, talk to your mom. You need to get it. Borrow it. I bet the Ricksmans have it. I mean, that's just a guess. When the sheriff began his pursuit, Robin Hood was already 7 miles out of Nottingham. Okay, this is what that looks like. They're not starting from the same place. Robin Hood is already out of town. So the sheriff has to overcome this difference. And we want to know, when did the sheriff catch up? So this is the distance that Robin Hood traveled, and this is the distance that the sheriff traveled. Sheriff of Nottingham. I'm going to write S of N, but not really, because that would just be too much. And there's the gap. That was Robin Hood's head start. Got it? Okay, so we can write the equation. The distance of Robin Hood plus the gap equals the distance of the sheriff. He had to travel so much more. And then let's rate and time it. Rate of Robin Hood, time of Robin Hood, plus K equals rate of the sheriff, time of the sheriff. I bet the Heplers have the Disney Robin Hood too. I'm guessing that the Saborans don't, because, you know, moving back and forth between the US and Asia, you get rid of a lot of extra stuff, right? Just thinking about that. When you move back and forth across the world like that, you tend to keep it minimal. So, you know, maybe Disney Plus. I don't know. That could be an option. I just really want you to see that movie. Okay, Now we make our list, right? And I go into my rant again about how I really want you to do it this way. But I already ranted once this lesson. I don't have to do it again. Okay, equal signs, because that makes me feel organized. Clock time. Am I going to need clock time? It doesn't look like it because we don't have any clock times in here. Let me read you now. When the sheriff began his pursuit, Robin Hood was already 7 miles out of town, so K equals 7. The sheriff traveled at 6 miles per hour, rate of the sheriff, while Robin Hood's rate was 2.5 miles per hour. What the heck? Okay, a fraction? Well, I'm not going to use a mixed number. So I can either use it as 5 over 2, or I can do it as 2.5. You have your choice as how you would choose to do that, but we're not going to use a mixed number. I'll tell you that right now. I can't decide which one I'll use. I'll mix it up in a minute. John uses the fraction, so maybe we'll just do that. So if you look in the book, you won't be confused. Okay, how long did it take the sheriff to catch up? Again, we're having to make an assumption that isn't really clear from how John tells how John tells the story. But the idea is that they took off at the same time. Now, how likely is that? This guy's what, 7 kilometers? Miles. 7 miles away. How would they start running at the exact same time? Overthinking, just say, fine, the times are the same. So what we can do is say that the time of Robin Hood equals the time of the sheriff, and the time of the sheriff equals the time of Robin Hood. And the easiest way to deal with that whole conundrum is just to use T. We don't have to differentiate between whose time because they have the same time. All right, that makes it easier, which is good because we have to deal with this drama. Let's make some buckets. Okay, rate of Robin. Let's use 5/2. Times, we're just using a plain T for the time, plus K is 7 equals the rate of the sheriff, 6, times the time of the sheriff, just plain T. All right, now I'll write this normally. 5/2 T plus 7 equals 6T. Oops. Now, first things first, let's blow up this denominator. We're going to multiply every term times 2. This cancels. We get 5T plus 14 equals 12T. All right, I like that. Subtract 5T from both sides. T's are over here. 14 equals 7T. John. So that means that the time it took the Sheriff of Nottingham to catch up using his superior running power is 2 hours. Now, that's kind of surprising if you follow the logic of the Disney movie. I mean, I've read the actual book of Robin Hood, but it doesn't stick in my mind like the Disney movie. And, you know, Robin Hood in the movie is a lithe little fox. And the Sheriff of Nottingham, I'm pretty sure, is like a big chubby bear. Which is not to say that people who are not skinny can't be super fit and fast, because they can be. But I find it very hard to believe that that kooky sheriff bear could run more than twice as fast and catch him in a matter of 2 hours. I find it very hard to believe that that chubby sheriff bear could run for 2 hours. I think he'd gasp and fall over. So, you know, we're gonna have to just suspend our disbelief and work with this. In any case, I hope you understood the math of this. I hope you kind of enjoyed these problems a little bit, because I think they're really fun. And I hope you have great appreciation for this lovely Robin Hood problem. And my last thing, I really hope that if you haven't seen that movie before, you watch it. Or, you know, what the heck, you guys, just watch it again. Have some popcorn, enjoy it, think of me and John, and I'll be happy. Goodbye.